In this video we'll be making a simulator for the modellpumpanlegg, the MPA. It looks something like this. I couldn't find a picture today, but this is the PNID, the piping and instrumentation diagram of it. It consists of two tanks of water, one tall one, with three pumps pumping the water from the tall one and up to the small one. From the small tank, well, it's actually bigger but it's lower, the water can run freely down to the tall tank again, and there's a manual valve in between so you can stop the flow manually. The tall tank has 5 level sensors, 5 capacitive sensors that senses if there's water in front of it. And we've given them some example names: level switch, level light. Each of the sensors have their own light connected directly to the sensor. So on the model, the light will light up if it's water above it, and this sensor will send a signal to the PLC. So we'll try to simulate that by making a simulated version of a water tank and another water tank and 3 pumps. So let's try that. In the mojo blocks there's some sim blocks with a tank simulation. We have some noise simulation, mass spring damper, which can be used for many things, and a curve if you want to play around with that, and a conversion from analog input and analog output. So we'll be using 2 of these for the 2 tanks, and yeah, let's just use that. So we'll need to add the library to the simulation part again. Earlier we added it to the Untitled one. Let's add it here as well. There we go. And I'd like a continuous function chart program, since this is short and visual. Let's add main sim so we can tell the difference. Then we'll add a tank. Let's call that tank 1. We have some parameters we could set if we'd like. A good idea would be to actually measure the height of the tank and the radius. Let's just leave that to 1. And then we'll add tank number 2. So those are our 2 tanks. Let's see what else we got. Yeah. We'll be needing a I/O list for the I/Os that we'll be simulating. Let's remove this. So let's see if we can find one already made. this one should do. Let's just copy paste all of this. So these are the inputs and outputs, all of them binary, for the PLC program that we'll be developing. So when we're making a simulator for that, we need to simulate all of these. We have to read what the program is outputting and simulate something that would create inputs that make sense. So let's add similar for this simulation. We add exactly the same. Let's make it pretty. But now we'll replace the inputs as outputs. So we'll receive the output from the Untitled 1 program, turn on pump 1, that's an output from there, but here it's an input, and then we turn on some flow and hopefully simulate something that makes sense. So let's replace all the I's with Q and all the Q's with I's. Let's just do some find replace. There we go, and then I's with, well, let's see how this goes. Oh, let's be more specific. %I with %Q. No, doesn't want to. There we go. And then %Q1 with %I. So now the pump command to pump 1 is an input to the simulation task. While from the PLC task it's an output. So we'll need to map those later. Now let's see if we can use this one. So if we turn on pump 1, there should be some kind of flow going out of the tank. So let's take a look inside this one. Oh, it's a compiled version, so we can't look inside. Let's just do the same for the other two pumps. So let's say these are all equally powerful. So this should give a 30% flow, and all three of them should give 100. So let's just make a new FC for that. We don't need any memory for it. It's as simple as it can get. If one of them are active, let's give 1/3, and if all of them are active, let's give all of the output. Let's call that pump calc, and it's as a function. Let's use text. Return type, let's use, well, we could actually you can assign many return types or many outputs of a function. That's possible. But here it's requesting one return type, and that's enough for this example, since we'll only be outputting a number between 0 and 100% based on the 3 inputs. So let's make that a real number. We'll have some inputs, let's say just call them x1, 2, 3. And if x1, then let's add a temporary memory, a temp real out. Even if it's said var, it would be var temp because a function does not have memory. A function block does have. Just for simplicity, this is always reset each scan, but in case you want to make it into a function block later. At first it's 0, and then we'll add if the inputs are true, and at the end we'll assign it to the return value. Let's use small letters. The semicolon here is not necessary in TwinCut, but it is necessary in Siemens SCL. So if you want to copy paste, just add the semicolon now and you don't have any issues. So if this one is true, then we'll add well, let's say 30. And let's make number 3 a bit bigger. So 30, 60, 100. Not allowed. Let's see if that's true. Seems okay. Let's try and add it here. In the opening percent, that seems to fit. Nope, that's on the outlet. Because the pumps are pumping out of tank 1. Let's see if that's gonna work. Should be fine. Then it should produce a level in percent here, liquid level in percent. Here's the exact in meters, and if you remember, it's all binary sensors. It's 0, 1. Either the water is below or it's above. So let's say 100% is completely full. 10% full, this one should be true. 20, 30, 40, 50, just to keep it simple. So we need to add a function there as well. Still don't need any memory, so let's make that a function. sensor calculation. Let's use text again. So now we'll be returning 5 Boolean sensor values, so this one doesn't really need to be anything, because we'll be adding an output struct. So let's add all the 5 sensors. And the input will be the water level. So the example, if x1 is greater than 10, then y1 is true. Otherwise it will be false. So since it's all temporary here and there's no memory, we don't need to set it to false, but let's do it anyway. Else it's false. And we use small letters. For number 2, whoops, sorry, number 2, let's use let's keep it 100% correct here, large letters. For number 2, let's say 20%, and number 3, 30%, and so on. And then the sensor 5, 4, and 3, that should do it. So if the input is less than 10, then y1 is false. If it's greater, it's true. So hopefully this should do it. Really don't need all of this. And we'll get the output pins here. So what should we call that one? Here it's called level switch low 1. That's the lowest one. And these are level indicators. Number 2, the numbering is 1 is the lowest, 5 is the one on top. Since these are level indicators, that should indicate that they don't really do anything, they just indicate the level. This level switch, something should happen when this is true or false, depending on what it's set up to be. LA, level alarm, high. This should then trigger some kind of alarm. But let's not worry about that at the moment. Let's just focus on the numbers. This is the lower sensor, this is the highest sensor, and these are the ones in between. So let's map those. The lowest one, I will switch low 1, X. If you would like to learn more about why these letters has been chosen, you can look into the ISA 5.1 standard for tags and PNID. high 5. So let's see if we can empty this tank. If we can initialize it. Start it. That didn't look right, so let's close and open. Yeah, it's not running because it's not assigned to a task, so let's do that. Remove this one, add this one. Let's activate that configuration. Ah, there we go. Well, then let's just call it var then. Clear those. How about now? There we go. So the level is now 0. Let's see if we can do something about that. You can set the volume. So let's set it to 50. 50%. That should mean the water is above all of these because the biggest number was 50. But then again, it's 100. So let's see what volume set. Yeah, that's probably in cubic meters. Let's set something smaller. .1, that resulted in our level at 3%. So let's say 1 then. 31%. Now let's see what happens if we mess with the inputs. Let's give a true value to all the pumps. Now it's decreasing. So that's good. We turned on all the pumps and the tank was emptied. That makes sense. And since it's empty, all the level indicators, all the lights should be false. So we've emptied the tank and all these lights are off. We still need to add a valve and a connection between the two tanks, both ways. So the pump flow should add water to tank 2, and tank 2, if the manual valve is open, should add water to tank 1 again. So flow out of tank 1 should go into tank 2. This one is in cubic meters per second, and this one is also in cubic meters per second, so that should work. And we'll need flow from this one into this one. And we could mess around with it, but let's just add some kind of restriction on the flow out and put it right back in. So let's add a variable for the manual valve xv1, unspecified valve 1. Make that a yield value and initialize it as 0. Then let's use a multiplier. This should be the flow into tank 1. Which is the flow out of tank 2 multiplied by xv1. So if xv1 is between 0 and 1, if it is 1, everything will be correct. If it's 0, everything that's going out of here, it's not going into here, so it's going somewhere else, which is on the floor, I guess. It will disappear, but it's gonna be good enough for now. So let's keep this one somewhere between 0 and 1 and see if it's 0, this one shouldn't fill up, and if it's larger than 0, it should fill up this one again. Let's see if we can initialize something other than 0. Let's try and put it at 1. And let's do the same for tank 2. See what happens. So the level now is 100% and 100%, so that maybe that's not a good idea. Let's leave this one at 100% and then leave this one at 0, which makes more sense, since if this one is open and these are off and this one is higher up, all the water in this one will flow back into this one. When this model was made, they made sure to make this one actually bigger. It's lower, but it's bigger than this one, so if you pump everything out of this one, it won't flow over. There's still room. So let's leave tank 2 to 0. That's the default value. And download so we can reinitialize, hopefully. Nope. Let's do a cold reset. Still no. Let's do a reset origin. There we go, 0. Just had to start it. So this is at 31, yeah, okay. Anywho, let's try and start one pump. Prepare that one and then pump. So the level went up and now it's going down again. Oh, that one's empty again because there's nothing coming out of it. Yeah, so that's not really good enough, is it? That was a cheap fix. Flow out of this one should be the flow into this one. Let's see if we can use valve out. See how this fits. So this one should be closed, so let's try and fill tank 2. And right. So the flow going out of tank 2 is 0. The flow going out of tank 1 is something, and then tank 1 is emptied. This one is not increasing because this one is empty, and it's not emptying anything. So let's mess with XV1. Let's say 10%. Stuff is happening. If we switch off the pump again now, there's no flow going out of tank 1 because all the 3 pumps are off. The level is increasing because this manual valve is 10% open, and there's still water in tank 2. Let's see if we can make it go faster. 100% open manual valve. There, that emptied it. Now the level is back at 31.8%, which means the 3 first load sensors are true. So that's how to simulate those 2 tanks. We've simulated the water level in tank 1 and tank 2. A simple simulation of the 3 pumps. If you turn them on, there's flow going out from tank 1 and up to tank 2. And a simulation of the manual valve. If it's closed, there's nothing coming through here. If it's open, there's more coming through it. And if you turn these off and this open, then anything in here will flow back into here and stay there. And at the end, all the water will be in tank 1 and no water will be in tank 2. We initialized it with a low water level, 31.8%, so it will never reach above these 2 sensors here because those are declared as 40% and 50%. Let's look at the I/O list again. So we've simulated these, that's the level indicators, and we've added some effect to these. When you turn on the pumps, flow starts to flow, but there's still a lot left here. So like these are feedbacks that pump 1, 2 or 3 are actually running. The simplest way to simulate that is just to say if we receive the command to run them, then they are actually running. As simple as that. So let's do that. Just map the command back as a confirmation that they are running. So where's the output? There it is. So pump 1 confirmed high. That's just the same as the command. And the same for 2 and 3. Whoops. It's not a very useful feedback. With this feedback we can confirm that we actually gave the command. It went through our I/O card and back into our input card. So it went through our output card and back into our input card, and that's about it. If we could place this one at the flow, so if we turn on pump 1, and the flow going out of tank 1 is something we'd expect by turning on pump 1. We can use pump 1 confirmed running as the flow is actually what we expect. And that means we've given the start command for pump 1 through our output card, from our output card through some other electronics to the actual pump, and the pump is rotating and moving water, and it's flowing where it needs to go. That's a better running confirm than just confirming that the command was given. So that's those three. Let's see what else we can mess with. These three are manual inputs. So there's a switch where you can lock pump 1 in outside mode, or remote mode, or local mode, or what you want to call it. So let's just leave that one. We can easily manipulate it like we just did in monitoring and then writing a variable to it. This is a command similar. Command high in outside mode, command low. This is the emergency stop button. This should always be high, otherwise something's wrong. We can also just simulate that one like these. These we have simulated. This is output to the emergency stop. So the way this one works is that we'll set 24 volts on one of our output cards, or two of them. There's redundancy here, and then wire that one to the actual emergency stop button. And if everything's okay and no one's pushed the emergency stop button, the 24 volts will return here. So that means that for the emergency stop to be okay, no one has pushed the button and the PLC is running, everything's okay, and the output card is working, so it's outputting 24 volts to the emergency stop. Otherwise, it's not okay. This one is for the light indicator on the emergency stop button, so let's not worry about that one now. Same for these are indications. We don't really need to simulate that one, those now. These are all for lights on the remote controllers. So let's try and program this. Let's do the mapping first. So we'll be mapping all our inputs in the sim task to outputs in the PLC task. So let's do that. One. Thankfully they're all alphabetical. Let's just map all of them. In case we want to simulate the remote controllers. And then the pumps, binary confirmed low, and all of these. There probably is an easier way to do this. It often is. Some kind of Microsoft Excel hack or something like that. But my rule is, if it takes less than 5 minutes to do, it's not worth making a script for it. And I'm only going to do this once, and it takes less than 5 minutes. So I'm not going to write any scripting for it. Whoops. On the Siemens equipment, there's a different way of entering all the variables in the I/O variables. and that's a bit more work and it takes more than 5 minutes, so I've done a script for that, which is just making an example here. This is what the Excel sheet made for the backoff type of declarations. And this is something that Siemens can understand, which is an XML sheet. That's a script combining all the necessary stuff. This part is actually, this code is actually in Norwegian, so it probably makes no sense at all. So kjede sammen is concatenate, if you can wrap your head around that one. So, I digress. We've done all the mapping. Should be okay. So now the SimPLC signals should be mapped to the Untitled 1 PLC signals. So let's program this. So this should be a working, good enough simulator for the MPA, and the next part is actually programming it. So this was creating a simulator.